AB Calculus Section 6.1, day number 1, velocity and net change. Objectives for today are to review the relationship between position, velocity, acceleration, connect position, velocity, acceleration to net area under a curve. So the first thing we want to do is ensure that that we know the relationship and I guess review the relationship between position, velocity, and acceleration. So let's say, for example, our position function is s with respect to t, as in time. Well, we know that s prime is the derivative of position, which gives us velocity, and s double prime, which is equivalent to v prime, is our acceleration. Now, using a slightly different notation, we can see right here that ds dt, which clearly would be the derivative with respect to t of s of t, is going to be velocity. And as you can see here, the second derivative of s with respect to t will be our acceleration. So you might see this notation for acceleration, or potentially you might see something with respect to s double prime or v prime. Likewise, with the derivative of s with respect to t, you might see ds dt or s prime of t referring to v of t. So how do we know if a particle is moving to the right or to the left? Well, we know a particle is moving to the right if v of t is greater than 0. And we know the particle moves to the left if v of t is less than 0. When it comes to speeding up or slowing down, a particle is speeding up if v of t and a of t have the same sign. Okay, guess I should have done that in green, but okay, whatever. Or slowing down, I'll go red, I guess. Slowing down if they have opposite signs. So if v of t and a of t have opposite signs. All right, fill in the blank. You can pause the video at this point, fill in these blanks, and now you have paused the video and filled in the blanks. If velocity is negative, the object is moving to the left, or potentially could be down, depending on whether the particle, its motion is taking place on the x-axis or the y-axis. Particle's velocity is positive, it will either be moving right or up. The sign of the acceleration is the direction of the force of the object. Okay, that's something we haven't touched on very often, and it doesn't come up often at all, but that's just something to be aware of. Number 4, an object is speeding up, okay, like we said above, if v of t and a of t have the same sign. Okay, and the object is, of course, slowing down. Very similarly, if v of t and a of t have opposite signs. All right, let's recall the difference between distance and displacement. So let's say I want to know the total distance traveled by a particle from time 0 to time 10, whatever the units might be. Well, I integrate the absolute value of v of t on that interval. This will give us total distance, whatever that might be, in meters or feet or whatever that might be. Displacement, however, is calculated by just taking the integral of v of t. So that takes any negative area and any positive area and simplifies it. Now, what's the difference between displacement and total distance? Well, total distance traveled, right, is exactly that, total distance. whereas displacement is considered the distance from original position. So here's a little graphic. Okay, let's talk about, I don't know, Tommy. Here's Tommy's house. Okay, Tommy's house. And here's Tommy's school. Their school. All right, Tommy travels at a positive velocity, or a distance of, let's say, 2 miles. Tommy then has a moment, pauses on the sidewalk, and says, whoops, forgot something. So he starts to head home. Heads home for 1 mile. Looks in his backpack and says, oh wait, never mind. And then heads back to school. Now, if this distance right here were, say, I don't know, 1 mile, his displacement would simply be the 3 miles from home to school. So it's the distance from the original position. His total distance traveled, though, however, is going to be much different. Total distance traveled, of course, will be the 2, then the 1, then another 2. Okay, so he actually traveled 5 miles. So he doubled back on that 1 mile loop when he had thought he had forgotten something. Okay, so that's the difference between total distance traveled and displacement. Let's continue with a few other examples. All right, graphically we can see distance and displacement. For example, on this velocity graph, let's say that this graph right here, that was freehand, so yeah, tell your friends. That's your velocity graph. Okay, so as we look at the equations that we talked about earlier, of course this would be displacement. So any area above the x-axis, let's call this first area A. And let's call this A. A would have a positive area. And then B would have a negative area. And then C. And C would have, again, a positive area. So to find displacement, we would simply take A's area minus B's area, and then plus C's area. All right, now this is under the assumption, right, that we're considering B a positive area. Now, if I were to consider B a negative area, I would say plus B, right? So the first is under the assumption that we say B is greater than 0. If I were to make this assumption and add, then I would be under the assumption that B is less than 0. So either way you go, you could either add negative value or subtract a positive value when it comes to displacement. Okay. So when it comes to total distance, what we do is we take the area A plus the absolute value of the area B. That's under the assumption that B is less than 0, plus C. Okay, so if A was, let's say, 10, and B was negative 12, and C was 15, right, our displacement would be 10 minus 12 plus 15, which would equal 13. That's our displacement. Our total distance would be 10 plus the absolute value of negative 12 plus 15. All right, which of course would be a bigger number. How about 37? Okay, now you might question, like, how could I tell the difference? Well, if you take 2 times the absolute value of the negative area, right, which would be 24, and I took 13 and I added 24, I would get my total distance. Okay, so let's look at a calculator active problem here. It says given that ds dt, which is v of t, equals t squared minus 8 over t plus 1 squared, find the displacement from 0 to 5. Okay, so what that's asking us to do is asking us to find the integral from 0 to 5 of v of t, right? Displacement, we would not use absolute value. So in your calculator, you're going to want to press math. Let's go through a little keystroke sequence here. Press the math button, and first of all, actually make sure you're in radian mode. So press mode, go down to, like, I think it's a third option. There's math, print, normal, float, and then radian. Make sure you're in radian mode. So press math, then press 8, and what should pop up on your screen, if you have a newer calculator, should be the integral notation with a bunch of little blanks. Okay, and anytime you see calculator active, the first thing you should do is you should plug your function in for y1. Okay, so I plug v of t in for y1, and I'm ready to go. Okay, so you should see a bunch of blanks like this. If you got an older model calculator, it's all good. We can talk notation a little bit. Plug a 0 in there, 5 in there, a y1 in there, and an x there. And then when you hit enter, let's see, what did I get? I got a displacement of 35 units. So the displacement from 0 to 5 of that velocity function is 35 units, meters, feet, whatever it might be. Okay, for total distance, what we do is, again, math 8. Okay, math 8. My dog's getting wild over there. Okay, you're going to see this again pop up. Okay, you're going to do a little something different in for the function. I'll show you in just a second. So you do your normal stuff, 0, 5, x. Now, what you want to do is, when inserting your function, first thing you want to do is math, and then you're going to go over to, there's an option along the top column. Where is it? Math, and then over to number, right? So go over to the number option, and then you want to select option number, I think it's 1. Yeah, actually, it's option 1, which should say abs, right? It says abs. What that's going to do is it's going to be your absolute value. So when you click enter on option 1, which is abs, you'll have that absolute value notation pop up, and then inside there you want to put y1. Okay, so then press enter, and you should get what I get, which is, to 3 decimals, 42.587. Okay, if you got an older calculator and you press math 9 and this notation doesn't pop up, you'll probably get some notation like this. That's numerical integration. Okay, and you're gonna want to do the following. It's going to pop up with some notation like this. In the first blank, right, there'll be a blank here. Well, actually, there won't be a blank there. You have to actually punch it in there. But you're going to put in y1. Okay, so if you're doing your displacement, you're going to put in y1. If you're doing total distance, you're going to put in, do the abs work there, and then put in y1. Okay, and then your independent variable, which is x, and then your limits, 0 to 5. And you should get exactly the same answers, right? You should either get 35 or 42.587, depending on which method you're using. Okay, so that's how you use your older model calculator to do that. All right, so in summary, if we integrate velocity, we get displacement. This is the net area between the velocity curve and the time axis. So, right, if I have velocity and time, and my curve looks like this, let's say we go from 0 to 5. All right, it's going to find that exact area. Now, if the velocity is always positive, what's interesting is displacement will always be equal to total distance. So in this situation, you would actually get 0 to 5 v of t in my graph shown here. the two would be equal, right? So imagine that Tommy walked to school and didn't turn around at all. Those two would be equal. It's when we get a change in the sign of the velocity where we'll get a difference between displacement and total distance. So like in this graph here, right? If I go from 0 to 5 here, clearly displacement and distance are going to be different. Okay, so be aware of that. And let's get into some examples. Okay, let's get into example 2. Let's derive the general equation of velocity. So it says if a particle moves with a constant acceleration of negative 32 feet per second, find the velocity of this particle. Okay, so we know that the integral of a of t is going to equal v of t plus some constant, right? So let's take the integral of negative 32 with respect to t, which would give us negative 32t plus, I'm going to call this c1. So this is velocity. So velocity is given by negative 32t plus c1. Now, just out of curiosity, what would v at 0 be? Well, v at 0 would be negative 32 times 0 plus c1. So v at 0 is actually c1. Okay, so now let's consider, continuing on, let's find x of t or s of t based on v of t. Okay, so we know that the integral of v of t is equal to x of t plus some constant. I'm going to call that c2. Okay, so the integral of x of t, the integral of v of t is the integral of negative 32t plus c1 with respect to t, which would give us negative 16t squared plus c1 times t plus c2. Therefore, we could say that our position is equal to negative 16t squared plus, recall that c1 is actually equal to v sub 0, or v of 0, which we'd call the initial velocity, plus c2. Now, check this out. If I plug in a 0 into this function, I would get negative 16 times 0 squared plus v sub 0, or the initial velocity, times 0 plus c2. So you can actually see the initial position ends up equaling c2. Thus, we could call this kind of your initial height, if you will, because as many of you know, this equation, those of you who are physics folks, this equation has to do with the position of a object based on the forces of gravity. So here's your initial velocity, and here is your initial height. And there you go. Awesome. Now, of course, that's in feet per second. If you're dealing with meters, this value changes, but it's all good. Let's look at example 3. Given a particle moves with an acceleration of a of t equals e to the negative t, what is its position and velocity moving along a straight line if it passes through the point 040? Okay, so this is giving us some information. This tells us that x of 0 is 40, and initial velocity, v of 0, is 60. Okay, so let's do a little bit of work here. Let's take the antiderivative of e to the negative t dt. Okay, that is, of course, taking the antiderivative of a of t dt. Okay, so if I take the antiderivative of e to the negative t, I get negative e to the negative t plus c. This is going to be our velocity function. Negative e to the negative t plus c. Let's solve for c by using the condition that I have here. At t equals 0, my velocity is 60, right? I get that directly from here. So our velocity is 60 when t equals 0, which, of course, we should be able to anticipate based on this, that 60 is equal to c. Thus, the velocity function for this particular situation ends up being negative e to the negative t plus 60. Whoops, I messed something up there, didn't I? Yes, I did. I'm good at math, I guess. Maybe you caught it, maybe you didn't. But C actually would equal 61. 61. Okay, you can see here I get negative e to the 0. Well, that's 1, so that's negative 1. So this is really 60 equals negative 1 plus c. So the initial velocity, as I goofed up earlier, is actually 61. Okay, so now let's find the position function. That's the velocity function. If you were to be asked, to find what direction the particle is moving at a certain time, you'd use that. Now let's find the position function by integrating that. So we're going to take the integral of negative e to the negative t plus 61 with respect to t. Okay, that's going to equal e to the negative t plus 61t plus c. This will be our position function, and I'm using x to denote position in this case. That'll be e to the negative t plus 61t plus c. So our initial position, we're told, is 40. So that'd be e to the negative 0 plus 61 times 0 plus c. So if that equals 40, I get 1 plus 0 plus c. Our initial position may have been 40, but c equals 39. Thus, our position function will be equal to e to the negative t plus 61t plus 39. And there you have it. You can be asked a number of different style questions regarding both your velocity and your position functions based on prior knowledge, okay? So we're just trying to derive those based on the information given. Let's continue with the next slide. All right, example number 4. I don't see anywhere here that I'm told I can use a calculator, so I guess we got to just grind some real calculus here. It says determine when the particle is moving to the right, to the left, and is stopped. Okay, so on this interval, if I were to consider values for v of t, right, we're going to use analytic methods here, which just means let's grind it. Okay. As you think about this function, right, t over 1 plus t squared, the only time on this interval from 0 to 3 that v of t will equal 0 is at 0, right? Otherwise, all values will be positive, even though as t gets larger, right, our limit as t approaches infinity of v of t, it will be approaching 0, right? However, it never gets there. The only time it is there is at time t equals 0. So I could technically say that the particle is stopped at t equals 0. But because v of t is greater than 0, when t, let me read that in a different way. How about when t is greater than 0 and less than or equal to 3? Okay, v of t is greater than 0 when that's true. Therefore, the particle is moving to the right when t is greater than 0. Okay, so it says find the particle's displacement for the given time interval if the initial position is 3. Or if the initial position is 3, what's the particle's final position? So find the particle's displacement for the given interval. All that's going to be, you guys, is going to be the integral from 0 to 3 of t over 1 plus t squared dt. Now, this is going to require us to use a u substitution. Okay, so I'm going to have, let's see, I'm going to set u equal to 1 plus t squared. Thus, du will equal 2t dt. Now, I almost see a perfect substitution, right? I see that t dt So therefore, what I need to do is I need to set 1/2 du equal to t dt. All right, so what that does to this integral, and I'm not going to work my limits quite yet, is I'm going to write this as a half, and t dt gets replaced with that 1/2 du, so I'll be left with 1 over u. Now, we need to change the limits of integration here. So if t equals 0, then, and knowing that u equals 1 plus t squared, then u equals 1. So my new limit, lower limit for this integral will be 1. If t equals 3, knowing that u equals 1 plus t squared, then u will equal, I believe that's 10. Yeah, that should be good. So we're going to, these two are equivalent, right? This integral here and our new integral over here are equivalent based on the change in our variable. Okay, so this will be 1/2 the natural log of the absolute value of u evaluated from 1 to 10. Okay, so recall that FTC part 1 requires us to take big F at 10 minus big F at 1, and big F just ends up being half ln of u. So I'm going to take half, and I'm actually going to factor out the half, take ln of 10, and I don't need the absolute values in this case, so it's kind of irrelevant, but I'll keep them anyways, because it doesn't really change anything. So I'll get 1/2 the natural log of 10 minus the natural log of 1. Well, the natural log of 1 is 0, therefore we get half the natural log of 10. Now, if there were a multiple choice question, this potentially could be listed as half the natural log of the square root of 10. All right, so this 1/2 can come up as a power of that argument. It could be written in either of these two ways, right? Either of those two ways. Okay, so that would be the displacement for that given interval. Now, knowing that, of course, we talked about up here, the particle is only moving to the right. It's not changing direction at all. Okay, the integral from 0 to 3 of v of t dt is equal to the position at time 3 minus the position at time, what would that be, 0. Okay, so this integral comes out to be ln of the square root of 10, right? That's equal to x of 3 minus x of 0. So since I know x of 0, or in this case it refers to it as s of 0, I'll just call it x of 0 just to clean the notation up a little bit. Okay, I could find x at 3, right? Its final position after 3 units of time. I would add this x of 0 over, so I'd have ln of the square root of 10 plus x of 0. Well, x of 0 is 3. So our position after 3 units of time would be ln of, I could write it as half ln of 10, or ln of the square root of 10 plus 3. And that would be my position, my finishing position, right? This would be my position at time t equals 3. All right, so find the total distance traveled by the particle. Since v of t is greater than 0 when t is greater than or equal to, actually I should say greater than 0, the total distance is actually equal to the displacement. And that's only because there's no sign change in velocity, at least on that interval. All right, let's continue on to the next slide. So just to be clear, both of those will equal the natural log, 1/2 the natural log of 10. Okay, let's move on and look at a few properties here. Okay, so here we've got some summary notes for position, velocity, acceleration. I would definitely look through these and read through them carefully. I'm just going to highlight a couple of things, and nothing new to you, but just recall that the position of an object moving along a line at time t is denoted as s of t or x of t. And that's the location of the object relative to the origin. So it's the number of units from the origin. Velocity of an object at time t is, of course, the derivative of the position. The displacement can be written in this way. So this will be the position at time b minus the position at time a is the change in position, right? So the area under the velocity curve is actually just the change in position. And the distance traveled by the object can be denoted using this notation, absolute value v of t. So go ahead and read through the remaining portions of this, and if you got any questions, please make sure and talk to your teacher. Let's continue on the next slide. All right, example 5, last slide for these notes for 6.1. It says the acceleration of a particle moving along a coordinate line is given by a of t is that thing. Okay, first of all, when I see calc active, the first thing I'm going to do is I'm going to plug my function right in for y1. So I'm going to set this thing equal to y1. Okay, so go ahead and do that on the side. I'll do it in just a moment here. If the velocity at time t equals 0 is 4 meters per second, that tells me v of 0 equals 4. Find the velocity 2 seconds later. So what I want to do, what I'm seeking, is to find v at 2. Now, algebraically, what you're going to want to do, you guys, is visualize this as the integral from 0 to 2 of a of t. Right? The integral from 0 to 2 of a of t gives us v at 2 minus v at 0. Right? Equivalently would be v of t evaluated from 0 to 2. All right, so again, extension here. We're not going to do that right now, at least yet. Let's get to the calculator. Okay, so just a quick side note. When you are doing a problem with this type of scenario, you are going to want to consider the displacement. Okay, you're not considering total distance traveled. Okay, so just be aware of that. Now, when I work through this, right, I'm going to do this calculation real quick on my calculator, and then I'll write out the value here in just a moment. Now, what do I know? I know v at 0 is 4. So if I want to find v of 2, I just simply have a linear equation to solve, right? I know v at 0 is 4. So I can find v of 2 if I have a value over here, which my calculator gives me 0.0226 75737. Now, you don't have to necessarily write it out this way, but what I would do, likely, right, is just write this as v of 2 is equal to the integral from 0 to 2 of a of t, provided we've defined it as a of t, that's good to go, plus 4. Right? Or if you're really paranoid about notation and you don't want to get docked, which you shouldn't here, right? The dt kind of closes this off, closes that off. So you're okay to tag the 4 on the end. Some people prefer to write it this way, just to like make sure that there's no question that the 4 is being added on the outside of the integral notation. Okay, I'm going to add 4 in this value, and to 3 decimal places I get 4.023. So that would be the velocity, 2 seconds later. Okay, I might go about this and just try to integrate this analytically. So I guess I'll do that. Let's go for it. Let's see if I can not screw this up. So 0 to 2 of, or algebraically, I guess. I'm going to write this again as 2t plus 3 to the negative third. Okay, dt. Okay, this is going to require a substitution, I believe. Like if I were to write it like this, it might make more sense why I have to do a substitution. This would be 1 over 2t plus 3 cubed. So, I mean, typically you're going to see your u nested somewhere, right? So it's a composition of functions. So I'm going to write u is 2t plus 3. So du is going to equal 2 dt. Well, I don't see a 2 dt, but I do see a 1 dt here. So I'm going to write this as half du is equal to dt. All right, so this integral becomes, I'm without a doubt going to run into some issues with space here, but that's okay. I'll make my work work. Okay, so when u is equal to 0, excuse me, when t is equal to 0, and I know u is 2t plus 3, I'm going to get u is equal to 3. When t is equal to 2, it looks like u is equal to 7. Okay, so now let's set this up. This is equivalent to the integral from 3 to 7 of 1 over u cubed du. And I got to tag that half in front, right? Can't forget that half. Okay, so where did it all come from? 1/2 du replaced dt. And of course, u replaced 2t plus 3. The rest just kind of sits there and hangs out and gets ready to be evaluated. Okay, so half integral 3 to 7 of u to the negative 3 du. Well, that's equal to negative, what would that be? Negative 1 over 2u squared. Yeah, that would work. Evaluated from 3 to 7. No, I forgot the half. Right? I forgot this out here. So I'm actually going to call that a fourth, right? All right, so now let's see if this works out. This is going to be negative 1 over 4 times 7 squared. Bracket that off. Minus negative 1 over 4 times 3 squared. All right, so that's going to be, this is going to be fun, is what this is going to be. All right, so it's going to be negative 1 over 4 times 49, 196, minus a negative, so that'll be plus 1 over, is that going to be 36? So let's see, 196 divided by 36. Oh, that's going to be gross. Lovely. All right, so that's just nasty. Let's just confirm that this is right. 196. Let's see if 1 over 36 minus 1 over 196 is equal to what we got. Oh my gosh, it worked. Okay, so it comes out with this answer. Right? So then, of course, you'd then have to determine, you'd have to set this value, 1 over 36 minus 196. This is not a good problem. I don't know why we would make you do this, but we are, and deal with it. All right, I just add 4 to that. So this would be 4 plus 1 over 36 minus 1 over 96 is equal to v of 2. And that value, this thing, it's worth it, right? Get a little repetition in, is equal to 4.023. Yuck. All right, let's continue with example 6. For the following problem, the graph of the velocity of a particle moving in the x-axis is given. The particle starts at x equals 2 when t equals 0. So x of 0 is equal to 2. Find where the particle is at the end of the trip. Okay, so let's think of it this way for A. Right, from 0 to 5 of v of t. That's equal to x of 5 minus x of 0. All right, so where is the particle at the end of the trip? Well, it's at its position at time t equals 5. So that's what we're looking for. So we need to find a value that represents this expression, which of course is going to be the displacement of the graph. And we need to know a value for its initial starting position, which we know. right, is 2. So we just have really an equation to solve for. So let's look at the area of the graph, or area trapped beneath the graph. So the integral, let's take the integral, go back to your pen, there we go. The integral from 0 to 4 of v of t. Well, that's going to be comprised of simply the area of a trapezoid, right? That's a trapezoid, boom, boom, boom. Okay, so that's going to be half base 1 plus base 2. Well, base 1 is the length of this, that's 4 units. Base 2 is the length of this base right here, that's 2 units. And the height, right, the height would be 2 as well. Okay, so that's going to equal, oh gosh, is that 6? Yeah, that's 6. Okay, so this value is 6. Okay, x at 5, right? Our position at time 5. Well, we don't know that yet, but we can do a pretty simple algebraic equation to solve for it. Right? So 6 plus 2 will equal x of 5, or our position at time 5. So it looks like the position of the particle after 5 units, don't know what that is, but could be any units, will be 8. Okay. Ooh, my bad. Wrong. Let's back that up. Mistake, Mr. Lud. Okay, I only went from 0 to 4. Way to go. I have to take away, right, or I have to add that triangle. Right, that triangle will just actually negate a portion of the original area under the curve. So the area from 0 to 4, I have to then add, right? So I'm going to take 6. That's not the value. My goodness. I'd have to add the area from 4 to 5 of v of t. Good catch. Okay, so it's going to equal 6. And we're going to take away 1. Is that 1? Yeah, take away 1. So the actual area that I get is 5. So let's change this slightly. This is not 6. This is 5. So 5. Boom. So our actual answer here for the where the particle is at the end of the trip ends up being 7. Okay, find the total distance traveled by the particle. Okay, that's pretty easy to do. Total distance traveled is going to be the area from 0 to 4 of v of t. The velocity is positive in that entire interval. So that's going to be, like we said, 6. And we're going to take the absolute value of the area from 4 to 5 of v of t. We know that that was -1, but we're going to take the absolute value of that and add those two values together. So we're going to get a total of 7 units. Okay, so that's it, guys. Interesting stuff with particle motion. Hope it went well. See you in the next video.